Let's do a quick review of the master method and talk about some of the limitations that exist. So first of all, we've been applying this to methods that are recursive, and typically they have the kind of the divide and conquer algorithmic style. So in pseudocode, kind of based roughly on the Wikipedia example, we've got some sort of a procedure. It takes input x of size n, and it does some work to determine if there's a base case and possibly solves the base case. Otherwise, it creates subproblems with a smaller size, n over b. And then it recursively calls itself multiple times to solve those subproblems. Then maybe it does some work to combine together the results of those subproblems. So we've parameterized this when we developed the recurrence equation. So we developed our parameter a that represents the number of recursive calls that occur. And of course, we already had our parameter b that represents how much smaller each subproblem is. We also have this concept of our function of the amount of work that's done at each call, at each instance of the problem, so f of n, which is composed of pretty much everything else here. So we could analyze everything else in this style of method by using the techniques that we've already used to determine our amount of effort required to solve our instance of a problem, the f of n. Okay, so we've also looked at graphical representations of these sorts of problems. So we described the graphical representation with the concept of a node representing the work being done. So we have a work that's doing some function of f work on a problem of size n. And we saw that this, when it recursively calls itself, we can describe that by drawing out basically a tree structure showing the recursive calls, and that there are multiple of those recursive calls going on. So the overall width of this, the number of recursive calls, or the branching factor, so to speak, is our parameter a. Okay, so a controls the overall width of this tree representation of the computation. And this would be very comparable to the, if we traced through running code, we could draw out what's called the call tree that would actually describe the execution of an algorithm. So A is really kind of about the width of this tree. B, on the other hand, controls how much smaller the problem gets, and we'll continue processing the problem until we get down to leaf nodes where the problem is essentially a base case. So B has an impact on the overall height of the tree. So it isn't the height, but it has an impact on the height. The closer B is to 1, the taller our tree will be, and the farther it is from 1, the more we'll subdivide our problems, and the shorter our tree will be. So by the way, we expect B to be greater than 1. We expect the problem size to diminish as we recursively compute. We expect to compute smaller and smaller problems, which will eventually lead us to our base case. Okay, if we think about those two factors and what their individual meaning is, one of them is about the overall width of the tree, the impact on width, and the other one is about the overall height. So together, in a sense, they kind of describe the amount of effort that it will take to build this tree. The wider it is, the more effort it takes. The deeper it is, the more effort it takes. Okay, so when we were looking at the equation form of counting our operations, t of n equals a times t of n over b plus f of n, the first part of this was really about the tree building effort. And the second part is about the amount of work that takes place at each instance of the problem. Okay? And our critical factor, again, is based on both A and B, which are really kind of measures of how complicated it's going to be to build that tree. So you can kind of think of that critical factor, log A over log B, as being a rough measure of the amount of effort that it's going to take to build that overall tree. Okay, so we had 3 cases that we were interested in, and all of them were about comparing this critical factor to the f of n function. So it's all about the balance of effort between building our tree versus the effort that takes place at each individual node. So we had 3 different cases. So case 1 is where the amount of effort at each individual node is below the amount of effort it's going to take to build that overall tree. Case number 2 is where the effort at each node is pretty much equivalent to that the effort it's going to take to build the tree. And the third case is where the effort at each individual instance, each individual node, is greater than the amount of effort it's going to take to grow the tree. Okay, so that's kind of a brief summary of the master method. Now let's talk about some of the limitations that you may encounter. So the master method doesn't apply to absolutely every problem of this form. So there are some assumptions that were built in. So we've been assuming that a is constant and that it's greater than or equal to 1. So we're assuming that the branching of the tree is constant, and that there will always be, if we branch, there will be at least one branch. There is no way to do a half a branch. So an example problem that looks like it might be something we could solve but actually violates this requirement is given here. T of n equals 4 to the power of n times our recurrence, t of n over 4 plus n. So where we fail here is in our a parameter, which is a function of n instead of being a constant. Okay, so we can't solve this with the master method. Another assumption that we've made is that f of n is positive, that it will only add time. So an example problem that we couldn't solve is given here, 5 times t of n over 3 minus n squared. So the minus n squared is actually kind of removing time, and that kind of violates our assumption about how f of n is actually going to impact computation time. Another assumption that we're relying on is that there's a polynomial difference between our functions, between our big O and big omega. So that we're either polynomially smaller in the big O sense or polynomially larger in the big omega sense. So what that really means is that there's some factor and some exponent, or that exponent's greater than 0, of difference. Okay, so in case 1, we're kind of assuming that there's some function of n difference below n to our critical factor and our f of n. Okay, so we're kind of assuming that f is polynomially smaller. If we can't demonstrate it's polynomially smaller, then we can't use the master method. So case 2 is about an exact value. Case 3 is about being larger than something, having a lower bound, an omega. And again, we're kind of assuming that it's polynomially larger. So we're kind of assuming that f of n is polynomially larger than n to our critical factor. So let's look at one more example. So consider this recurrence, t of n equals 2 times t of n over 2 plus n log n. So this looks very familiar to us. So we've got our a factor, our b factor, they're both 2, and we've got our f of n, which is n log n. Okay, so our critical factor, log of a over log b, is 1. Okay, and if we look at our f of n, this looks kind of promising. It looks like the f of n is n log n, which is greater than n to the first power, right? Because we're taking n to the first power and multiplying it by something that'll be positive as n gets large. So it looks like this might fall into case 3, that we might have a lower bound of n to the first. Okay, but remember that not only do we have to have a lower bound, but it has to be polynomially larger. And this is not polynomially larger, so this factor here is not some n to some power. Okay, so because it's not polynomially greater, the master method does not apply to this problem. Okay, one last thing to mention. Sometimes when we're working with equations like these, it can be really handy to go back and forth between having some exponent on a versus having some exponent on n. So particularly as we're trying to do these comparisons to see if something's polynomially smaller or larger, we would certainly like to express it in terms of n. Okay, so sometimes it's useful to change the bases. So I'm first going to talk about kind of a side problem, and then we'll come back to how we can do the types of transformations that we may need to do here. So first off, let's assume that we want to convert log base b of n to base a. So we can use the properties of logs. So we can just divide by the log base b of a to transform log base b of n into log base a of n. Okay, so this is just a common property or law of logs. Okay, and then we can rearrange that equation a little bit. So let's imagine that we multiply through by the denominator, and then we'll get an expression that will give us an alternate way of representing log base b of n. So log base b of n will be log base b of a times log base a of n. Okay, okay, so we are going to use this to our advantage. So again, we've got that relationship that represents the log base b of n in terms of the log base b of a and the log base a of n. And assume that we have a to some exponent, log base b of n. We can expand that out. So here is our log base b of n, which we know represents this. We can simply replace the exponent with an equivalent expression. Okay, and then we can do a little bit of rearranging of this. So let's go ahead and swap the order of the terms. Let's just move the expression that's log base a of n first. And the reason that's kind of convenient is because we now have a to some power that's based on a log of a. And if you remember, exponentiation and logarithms are kind of reciprocal complementary operations. So, and also we've got product of two exponents, so we can kind of factor that out. And now we've got a to the power of log base a of n, all of that to the power of log base b of a. Okay, so the expression in the parentheses there will basically cancel out. So the log base a of n is a way of representing a, if we take a to the resulting exponent. So that entire expression basically gets replaced with n. So we end up with n to the power of log base b of a. Okay, where this leaves us is we've got this relationship where if we have a to the power of log base b of n, that's equivalent to n to the power of log base b of a. So we've got a way of transforming an expression in a to an expression in n and vice versa.